We've been working with integrals, and in the beginning we let them represent the area between the curve and the x-axis. Think back to when we would make rectangles or trapezoids, and that's the visual representation of what an integral finds you when it comes to a function. An integral can also mean the antiderivative. That's kind of the how we calculate it. We take the antiderivative if we can. This final way of looking at integrals is talking about how it applies to real-world applications. So an integral of a rate will tell you how much, how far, or how many. One of the most common ones that we see and have worked with back in maybe chapter 3 or 4 is if you integrate velocity, that is how fast you're going, it will give you your position, and we oftentimes would call it S of t back then. I will let you know that a lot of times in this section, for this book's marking, they use x of t as position. So one of the easiest ways to remember that is when we talked about our Rudolph example long ago. If we, let's say, had Rudolph with a velocity graph of like 3 meters per second. If that was his velocity, a nice constant one, and someone said, well, how far did he travel from 2 seconds to 8 seconds? We would just take the 6 times 3 and get 18. So it represented that area. That's how we started. Well, you can integrate velocity, which is how fast you're traveling, a rate of travel. We can integrate other rates that apply to the real world. So let's take a look at a couple of those. In the exploration for 8.3, they're talking about water being drained from a swimming pool. And it's representing R is how much water is in the pool, measured in cubic feet at any given time. So R prime is the rate at which the amount of water is changing or leaking out of the pool. So when they say they want to integrate the rate that the water is flowing, and we'd find R of B minus R of A, that would tell us how much water is in the pool. Not how much water is in the pool, sorry. How much water drained from the pool. And that'd be over the time span of A to B. Over the interval A to B. So that's just how much water has leaked out since the time that they started at A to the time that they started at B. Always important to remember that your units, that would be in cubic feet. So when you're doing these story problems, as always with math, there'll be some units involved. So now we're going to look at a table. This takes us back to that idea of when we used to use rectangles for the area under the curve or trapezoids. We're given a velocity of a particle. So it's how fast a particle is traveling at any time. These are little snapshots, if you will. They want us to approximate the value of the integral of velocity from 0 to 30 using a midpoint Riemann sum. So here we're going to tie in our first idea of integrals being area to our now idea of integrating velocity, and we'll talk about what that finds us. So my first recommendation would be to plot a sketched graph. This will give you a better idea of what the data looks like. So this tells us, and remember this is your velocity graph, at 5 seconds the particle is traveling 1.6 feet per minute. Now, they want us to evaluate the integral of velocity. Remember we said if you integrate velocity, you get your change in distance. So, basically your displacement, that is, remember how far you started from the beginning. And so when we integrate velocity, we don't have an equation. We can't antiderive it. We have to find the area. They want us to use 3 equal size segments going from 0 to 30. So here's where I'll start at 0. And to get to 30, it would make my 3 increments if I cut it at 10 and 20. So for the midpoint, halfway between 0 and 10 is 1.6. There's my rectangle. 15 is halfway between here. And 25 is halfway between that last increment. I simply need to find the area of each of these rectangles. So my base on all of them is 10. And my heights are all based on these middle numbers. So 1.6 plus 3.1 plus 1.6. There's my base times all my heights. This area gives me a total of 63. Now remember units. So if velocity was the feet per minute, when we antiderive velocity, it will give me the amount of feet that that particle has traveled from 0 to 30. So if the integral of velocity is position, or your displacement, when they want us to integrate acceleration, that's going to give us the velocity that it has changed over from a certain time span. So in this case, we don't have equations again. We can't antiderive an equation and plug in 25 and plug in 5. But we know the antiderivative of acceleration is velocity. So this will equal the velocity at 25 minus the velocity at 5, just as when you take the antiderivative, you plug in the top one minus the bottom one. Our velocity at 25 is 1.6. Our velocity at 5 is also 1.6. So we get 0. Now, remember our label. We just found a velocity. So that is feet per minute. What did this tell us? Well, the change in velocity from 25 minutes to 5 minutes was equal. So we know the velocity was the same at both 25 and 5 minutes. So another example in your packet talks about a pan of cookies being removed from the oven and then the rate at which they cool. Whenever you're given information in a problem, especially like AP tests will do this for you, a lot of it is not just fluff. So the temperature of the cookies is 100 degrees right when they take it out. So that's like our initial condition. That's something important to keep in mind. Now, the rate at which the cookies is changing is this B prime equation. The value of B prime means we're just going to plug that number in. So B prime of 3 would be our negative 13.84. And then plug in our 3. So you'll have a calculator and you can plug it in and get your value, which is negative 8.236 degrees Celsius per minute. That means that the cookies are cooling at a rate of about 8 degrees per minute when it's 3 minutes in. So it asks you to sketch a graph on the axis below of this graph without a calculator. Now, that means kind of expecting us to remember that an exponential starts out slow and then increases. That's its parent function. Since it has the negative in front of it, it's going to flip over. So it would kind of increase. Instead of being up like this, the negative flips it over the x-axis. So when this happens, what is it saying? That when we have the cookies and we first take them out of the oven, the rate at which they're cooling is more intense. Like it's going to be going down like 10 degrees per minute, or then 8 degrees per minute, or 6 degrees per minute. As time goes on, they're not as hot, so their rate of cooling isn't as intense, if you will. It won't be cooling as quickly because they're already quite cool. Now, there's probably a threshold here where the cookies aren't going to cool anymore, like once they've been on the counter for a long time, so it approaches that value of 0. It's basically going to stop changing temperatures. Finally, for C, at time 10, what is the temperature of the cookies? So what, or how much, or how many? So if we know that the rate is that B prime, if we integrate the rate, and when it comes to an AP test, you don't have to write all of that equation out if you don't want to, but it is important that you write this. We want to know how cool are the cookies? What is the actual temperature in 10 minutes? So if we integrate the rate at which they're cooling from 0 to 10, we will get how much the temperature has changed. This will give us how much the temp has changed over those 10 minutes. So when we do that, we would use our calculator and find our solution to be negative 65.817. Notice the 3 decimal places as good practice for the AP exam. Now, that is how much the temperature has changed in 10 minutes, but they ask what the final temperature is. Remember, first of all, it wouldn't make sense to have a negative 65 degree cookie. So we have to remember the initial amount. We could add this on the initial amount of or degree of the temperature. Sorry, the degree of the cookie is 100. So if we combine these, we will get our total to be 34.8 0.183 degrees Celsius. And that will be our final temperature. A quick glance at one more problem in your packet. We have the rate at which people are coming into an auditorium for 2 hours. We also know that 100 people were already in the auditorium before they opened the door. They ask, how many people are in the auditorium when that concert begins at 2 hours when they shut the door? So if we integrate the rate, we will get how much or how many are in the building. So we'll integrate from 0 to 2, but we have to remember that 100 people are in the building, plus the how many people will enter from the time from 0 to 2, and that will give us our final answer. You would want to use a calculator for this one, and if you did, you would find the total number of people to be 1,080. Try that on your calculator so you can check your math. This will definitely be a very likely AP test problem. I suggest or encourage you to try these AP problems at the back of your packet.